Picture this. You're cruising down the highway in an electric vehicle. Inside that motor, components are screaming at upwards of 12,000 RPM. Now imagine if, in a split second, that motor just mechanically locked up or completely lost its electromagnetic sync. I mean, the physical forces involved would be absolutely catastrophic, right? Well, welcome to today's Explainer. We're diving deep into a hidden battleground in EV engineering, the A07 motor stall and shaft-locked fault. We're going to unpack exactly how engineers detect this disaster, how they mitigate it, and ultimately how they design it completely out of existence. And the craziest part, it is a literal race against a 60-millisecond clock. Here is our roadmap for today. We'll start with the anatomy of a motor stall, then move into the smart diagnostics and fallbacks, look at the hardware design, the manufacturing process, and wrap up with the ultimate validation torture tests. All right, Section 1, Anatomy of a Motor Stall. The physical destruction. Because before we can talk about the cure, we really need to understand the disease. What is physically breaking inside that motor? Well, it boils down to 4 distinct physical root causes. First, you've got bearing seizure caused by EDM, or electrical discharge machining. Second is rotor seizure. This is where physical friction and high-speed sweeping literally cause the components to just grind together. Third, we have electromagnetic stall, often called pullout, where the magnetic fields completely lose synchronization. And finally, locked rotor thermal overload. That's when a physical jam forces the motor to stall while drawing massive current, and that extreme localized joule heating can melt the coils in seconds. Now let's talk about the invisible threat behind that first cause. Look at these numbers, 70 to 370 volts. Modern EV inverters use advanced silicon carbide MOSFETs that switch incredibly fast. And that extreme voltage change induces high-frequency common mode voltages right on the motor shaft, peaking anywhere in that 70 to 370 volt range. If that voltage breaks down the lubricating oil film in the bearings, you get EDM. It's basically tiny lightning bolts shooting through the bearings, pitting the metal, burning the grease, and eventually, total mechanical lockup. The third cause, the electromagnetic pullout, is just wild. This happens when the motor's software basically loses track of the rotor's physical position. If the calibration is off, or if massive acceleration causes deep magnetic saturation, the electrical angle estimation can lag by more than 15 degrees. When that happens, the magnetic alignment just falls apart. Torque violently drops to literal zero, and the whole drivetrain gets hammered with alternating negative shocks. Okay, moving to Section 2, Smart Diagnostics and Fallbacks. The system's reflexes. Once a stall triggers, destruction is right around the corner, so the software has to act fast. And when I say fast, I mean 60 milliseconds. According to rigorous ASIL D safety standards, the car has a fault-tolerant time interval of just 60 milliseconds to save itself. Guys, that's less time than it takes to blink. In that microscopic window, the vehicle has to detect the anomaly, verify it's not just a sensor glitch, and execute a complex fallback routine to stop the motor from tearing itself apart. So how on earth does it do that? Through a doer-checker architecture. Think of it like a pilot and a co-pilot wrestling for control. If the motor jams, the primary core, the doer, tries desperately to spin it, pushing its control loops to 100% saturation. Meanwhile, the checker, secondary core, is independently watching. If it sees maximum effort but zero actual speed, it aggressively raises the alarm. And to make sure it's not a false alarm, it cross-references multiple sources: the main resolver chip, a software observer model, and the actual physical wheel speeds from the chassis. Now, what happens next is fascinating because the car's fallback strategy totally changes depending on how fast you're going. If you're moving slow or stopped, the system triggers an active open circuit, or AOC. It immediately cuts all power to prioritize thermal protection, basically stopping the coils from melting. But if you're flying down the highway and the motor jams, instantly cutting power would cause massive, uncontrollable voltage surges from the spinning magnets. So instead, the system prioritizes dynamic stability with a stepwise active short circuit. This stepwise ASC fallback is just a masterclass in electrical engineering. Step 1. The software initiates a 2-phase short circuit to absorb the violent initial shock. Step 2. It intentionally waits exactly 1.5 milliseconds. Why? Just long enough to dodge the absolute peak of the voltage surge. Step 3. It triggers a 3-phase lower switch short circuit. This bleeds off the kinetic energy safely and clamps the voltage under 720 volts, protecting the whole high-voltage system from a fiery overload. It's amazing that software can save the car in 60 milliseconds. But you know what's better? Stopping the fault before the software even has to wake up. Let's shift gears from reacting with software to proactively preventing it with physical hardware design. Which brings us to Section 3, DFMEA, Engineering the Design. This is where we identify potential failures and physically design the problem out of existence. Remember that electromagnetic pullout we talked about? To prevent that, engineers actually embed physical search coils directly inside the motor slots. This is foolproof algorithmic redundancy. Since they are completely decoupled from the main power windings, they aren't affected by intense heat, resistance changes, or magnetic saturation. Even in a massive stall, these search coils provide a clean, independent backup signal of the rotor's exact angle. And to stop physical friction or rotor sweeping, engineers demand absolute extreme precision. They limit the dynamic runout, basically the wobble of the spinning rotor, to less than 0.05 millimeters. By holding tolerances that microscopically tight, they literally engineer out the possibility of the high-frequency mechanical sweeping that causes hardware lockups. All right, Section 4, PFMEA, perfecting the process. Look, you can have the best design in the world, but if the factory builds it wrong, it's still going to fail. This quote right here really says it all. Comprehensive prohibition of manual hammering and pneumatic press fitting. Why so strict? Because hitting a bearing with a hammer creates invisible, microscopic dents in the bearing races. Instead, the factory has to use automated concentric servo presses with real-time force and displacement monitoring. If that machine detects even a tiny pressure anomaly, it physically locks down. That compromised bearing is never making it into a car. And preventing thermal meltdowns. That starts on the assembly line too. Factories use torque angle servo fastening paired with actual optical character recognition scanners. The cameras physically verify that every single bolt has the right phosphate coating for standard friction. Then, the servo tools precisely measure the rotational force and the exact angle of the turn. It guarantees perfect axial pressure on every connection, preventing the micro-resistance that leads to electrical fires. Finally, Section 5, DVP and R, the ultimate validation. We've done the theory, the software, the design, and the manufacturing. Now we torture test it. And this testing matrix is absolutely brutal. First up, thermal overload. They literally lock the motor shaft in place, cut the coolant, and blast it with maximum peak current. The system has to detect the stall and kill power in under 5 seconds, keeping insulation intact. Next, to prove the bearings won't fail from EDM, they bake the motor, shake it with intense 3-axis vibration for 500 hours, and hammer it with high-frequency voltage switching. And for the grand finale, they spin it at a screaming 12,000 RPMs on a simulator and inject a total mechanical lockup. The software has to step in within that magic 60-millisecond window and keep the voltage surge under 720 volts. It only goes into your car if it survives all of that. From the physics of shaft voltages to those 60-millisecond software reflexes, all the way to the robotic precision of the factory floor, stopping an EV motor stall is just a triumph of modern engineering. These multi-layered systems are basically invisible safety shields, constantly calculating to keep you safe at highway speeds. It really makes you wonder, right? With this level of obsessive engineering protecting just one component, what other incredible engineering miracles are happening right now, silently under the hood of your EV? Keep learning and stay curious.